right, let's try this one again. See if we can make it through without the recording failing. All right, so tension is another example of reactive force. Tension is the force that pulls through something like a rope or a chain or a cable, and is used to transmit force. So we'll see later, even if we use a pulley and we change the direction, we're looking at the same force in the line. In this case, if we have something just hanging from a string, then tension is the force that's going to be pulling up and giving support, and then the weight of the object is going to be trying to come down. So what we're looking at then is that tension is, in this case, because it's nice and simple, just one rope, is equal to the weight of the object. Now, hopefully you saw this coming because we've already done a couple of questions like this. You don't have the weight of the object. What we have is mass. Not only that, though, we have this mass, and it's not even the type that we normally like, right? We like kilograms because we know how kilograms work with gravity and turn into newtons. So we'll have to fix that. We can still deal with it. We've used this trick before a couple of times, but we can put together mass and gravity, and we can build in a conversion while we're doing the work. And in fact, we have a couple of options on how we can show this. You can technically treat the whole thing like it's just a conversion, or you can go back and sort of build it in at the end. So if we look at this from here, again, we have our way in, we have mass. I'm going to stack it like a fraction, just so it fits a little better with our strategy. So I'm just going to put that over 1 for free so that it lines up. Then we know we have to get to kilograms because that's how gravity works, at least the number we know for it. So we have to have grams on the bottom and kilograms at the top, so the G will cancel and give us kg here. And remember, kilo or K means 1,000, so 1 right there makes 1,000 of these. And then here's the part where we have some options. Technically, this converts the mass into an appropriate value, but if we want to, we mentioned this, it's not perfect, but we can build it in line like it's a conversion. We can say how kilograms turn into newtons because of Earth gravity. 1 kilogram makes 9.8 newtons, with the assumption that you're on Earth at roughly sea level, but we usually are. So let's check our units, make sure everything's going the way we want, because we're trying to get to newtons here. We see that grams can cancel with grams, and kilograms cancel kilograms, and so newtons are left, and yeah, looks great. It's exactly what we were looking for. All right, so now we want to run through and evaluate with these. The denominators are easier to deal with. 1 multiplied by 1,000 multiplied by 1 again. Should be obvious that not a whole lot's going on there, so we still have 1,000 on the bottom. On the top, we want to multiply those together, and we get kind of a big number to start with, but we'll fix that in a minute. We have 4,458.51. Okay, and then that's over 1,000, and if we look, the only units that survived were newtons, so whatever this answer is turns into newtons. Well, it's kind of nice because there's 1,000 on the bottom. You can just slide a decimal around. Or even if you put it in the calculator, it should be relatively recognizable. And because this will be the final answer, we'll go ahead and round now to 2 decimal places, but this turns into 4.458, so on, which we can reasonably say is about 4.46 as a final answer.